The title of our final presentation is Biomass Fuels as a Renewable Energy Source in Manufacturing Process Heating. Today, sustainable energy strategies have become a trend amongst a large number of manufacturers. Fossil fuel technologies have been the primary source in order to meet thermal energy requirements in manufacturing industries in the last 2 decades. The common substances used in fossil fuel energy manufacturing are oil, coal, and natural gas, which are unsustainable and contribute to global warming. However, powering manufacturing processes with biomass fuels can produce less greenhouse gas emissions, environmental pollution, while saving depletable fossil fuels and being carbon neutral, since growing biomass can help absorb carbon dioxide emissions. Thus, our group proposes to adopt the biomass gasification system in order to replace the current fossil fuel heating process. To indicate the overall performance of the gasifier system in relation to the existing fossil fuel system is the amount of biomass used to replace a liter of diesel. A simple calculation based on mass balance would result in the biomass fuel costing to about 25% of the fossil fuel cost. According to fossil fuel cost, 1 liter of fossil fuel, which is 0.42 USD per liter, can be replaced by about 3.5 kilograms of biomass, which is about 32 USD per ton, which significantly minimizes the material cost. Moreover, the amount of carbon dioxide saved in manufacturing industries in the US will be about 6,500 tons. Along with the carbon dioxide, large amount of other pollutants such as sulfur oxides and nitrogen oxides are also in a much lower concentration. Even though biomass fuels create a lower concentration of pollutants than fossil fuels, there are still limitations that have been found in existing biomass gasification systems. One of the current limitations is a high amount of tar and pyrolysis products being produced because pyrolysis gas does not pass the hearthstone. This requires extensive gas cleaning. Another limitation is the decreasing efficiency of biomass plants compared to fossil fuel plants due to the buildup of contaminants and deposits in the superheating tubes. Contaminants such as potassium, chlorine, sulfur, and sodium, which are often contained in biomass fuels, can deposit on superheater tubes after being exposed to combustion exhaust gases. These deposits in their molten state can lead to accelerated corrosion of the superheater tubes, thus decreasing their efficiency faster. In order to reduce the corrosion of the superheater, the temperature of the process is reduced. However, by doing this leads to a lower energy production efficiency. In order to minimize these problems, approaches that aim to reduce the production of tar and pyrolysis products, as well as to reduce contaminant deposition, need to be implemented to the current biomass gasification systems. Our team will tackle the problem from 2 consecutive stages of biomass heating: biomass gasification stage and the biomass boiler stage. In the first stage, where the biogas is generated, improving actions such as implementing biomass pretreatments and biofuel syngas purifications are considered in order to reduce solid and gaseous waste. In the biofuel boiler stage, actions such as pre-coating the heat exchange tubes and removing corrosive components such as potassium chloride from biofuels are taken in order to prevent the buildup of the superheater contaminants. Optional boiler structural improvement methods also could be incorporated for the optimization purposes. The biomass gasification process, pressurized entrained flow biomass gasification, also known as PEBG, is a technology that is commonly used by the majority of manufacturers. This process generates gaseous fuel by heating wooden or agricultural biomass inside a gasifier. Although this large-scale gasification system can supply heat in a large scale, this process also requires a very high temperature environment, which often causes soot formation and ash accumulation. The team suggests preheating the biomass with alkali impregnation with sodium before being processed by the PEBG system. This process will increase the char gasification rate, improve tar decomposition, and decrease tar formation. The biomass pretreatment will increase the sulfur capture rate by 20 to 40% compared to the non-impregnated materials. The product gas generated from the biomass gasification also needs to be further processed in order for effective utilization. Gas cleaning is a critical part of the system, which is applied in order to avoid corrosion, erosion, and environmental problems in the downstream equipment. The product gas mainly contains particulates, tar, alkali compound, and nitrogen and sulfur containing compounds, which need to be removed before the product gas is used. Cyclone separators are taken account to be used to separate larger particulates above 5 micrometers in diameter at the initial cleaning stage. As well, wet scrubbers will be installed to remove particulates using liquid sprays on the gas stream. It can remove 95 to 99% over 1 micrometer particle size and 99% of over 2 micrometer particle size. Followed by that, the team will build electrostatic precipitators in order to charge and separate the particles by applying an electrical voltage. In the final step, barrier filters will be adopted in order to allow the gas to pass through various porous media, collecting the particulates of 0.5 to 100 micrometers. Considering the biomass gasification is processed under high temperatures, packed bed filters to use bed materials such as ceramic spears and sawdust, which have been tested in a gasifier operated at about 700 degrees Celsius gas temperature in order to capture smaller particles of even sub-micron size. As well, a simpler and cheaper filter is also considered to be installed to purify the gases. The filter will have 2 layers. The outer layer will be made out of zinc oxide, which is aimed to capture the remaining sulfur from the previous processes, and the inner layer is made out of carbon in order to absorb tars produced in the upstream steps. In order to mitigate corrosion of the superheaters in the biomass gasification systems, modifications to the current system including using sulfur additives, optimizing boiler design, and optimizing the steam temperature are included. Most corrosive materials found in biofuels are the chlorides, such as potassium chloride. Additives such as ammonium sulfate can remove chlorides from superheater deposits and reduce superheater corrosion rates by 50% by converting alkali chloride deposits to less corrosive alkali sulfite deposits. Boiler modifications such as adding a radiant pass between the furnace and superheater, installing cooling tubes directly upstream of the superheater to trap chloride deposits, and adding a superheater insulation layer to increase the surface temperature above the dew point temperature of alkali chlorides can also be implemented to reduce corrosion. As well, the steam temperature should be optimized so that the maximum temperature achieved with the lowest total energy and maintenance costs is sustainable. These modifications will require testing and optimization based on the properties of the boiler and will aim to optimize the boiler's lifetime and efficiency. Advanced manufacturing technology such as nanotechnology has also been introduced into preventing the corrosion due to its ability to enhance both mechanical and physical properties. There are 2 methods, which are top-down and bottom-up. Both methods aim to develop a nanocrystalline coating above the superheater tube. For the top-down approach, it aims to generate a nanostructured alloy along with the pre-existing material. For example, the surface mechanical attrition treatment benefits from the milling ball impacts, which contributes to the grain refinement induced by plastic deformation. In this treatment process, plastic deformation occurs in the surface layer because of the strike from the multi-directional flying ball. The nanostructure is generated under a high strain rate. Also, the nanograined layer, which is made of pure zirconium, is relatively stable in a high-temperature environment. Another approach to improving the biomass superheater is to pre-oxidize the walls of titanium-containing alloy tubes, which is also known as mnemonic 80A. This pre-oxidization process initiates the formation of the titanium-chromium-rich oxide on the alloy. This lessens the interaction between titanium dioxide in the oxide and potassium chloride in the biofuel during the initial stages of corrosion. This will thus protect the surface of the tube from corrosion without lowering the combustion temperature. The bottom-up method places emphasis on the formation of nanocrystalline from the nanocrystalline powers such as the HVOF process or spray-based processes. Furthermore, the coating can be formed through growing nanocrystalline layers directly on other layers. For instance, after eliminating the potassium chloride from the process, the sulfur dioxide can be introduced into the gas phase to reduce corrosion. Sulfur molecules gather around the lowest part of the corrosion area and along the attack boundaries, which cause the formation of chromium oxides. The formation of chromium-rich oxides can slow down the superheater corrosion. Then, in the gasifier, the sulfur dioxide can be introduced with secondary combustion air after removing the potassium chloride substances in order to reduce the corrosion without decreasing the efficiency of the superheater. For design review and future work, extensive research of scientific papers and summarization of lab-scale experimental results of the proposed solutions that we previously mentioned, as well as their advantages, estimated improvements, as well as limitations, are listed in a table as a summary. Modeling and testing of each individual improvement will be required. Processes with low efficiency, significantly complex setup, or higher costs could be potentially eliminated. Then, the selected improvement steps can be incorporated together and modeled as a complete system. The construction and evaluation of these steps would require extensive laboratory resources and use of computer-aided design and simulation tools. After optimizing the processes, an overall cost efficiency and design for environment maintainability analysis should be performed, where a final design stage could be reached.